Welcome to week 3 of Health IT Databases. This week, we're diving into one of the most fundamental concepts in database design, normalization and data integrity. If week 1 introduced you to database management systems and healthcare coding, and week 2 covered ER modeling and relationships, this week is where we learn how to design databases that actually work well in practice. Databases that don't fall apart when you try to add, update, or delete data. By the end of this week, you'll understand why some databases are a nightmare to maintain while others run smoothly for years. The difference often comes down to the concepts we'll cover today. Let's look at what you'll be able to do by the end of this week. First, you'll be able to define functional dependencies and use their notation. This is the theoretical foundation that drives everything else we will discuss. Second, you'll learn to identify the 3 types of database anomalies: insertion anomalies, update, and deletion anomalies. These are the problems that arise from poor database design. And in healthcare, these problems can directly impact patient safety. Third, you'll apply normalization rules, specifically first, second, and third normal forms, to transform problematic tables into well-structured ones. We'll use healthcare data from our X-Health primary care database throughout. Fourth, you'll implement data integrity constraints in Postgres. This is where theory meets practice. You'll write actual SQL to enforce the rules we discuss. And finally, you'll understand HIPAA, de-identification requirements, and how database design supports privacy compliance. This connects directly to your work as health informatics professionals. Let's begin with part 1, functional dependencies and database anomalies. This is where we'll establish the foundation, the functional dependencies and the problems they help us solve, database anomalies. Think of this section as understanding why before we learn how. Once we see the problems that poor design creates, the solutions we cover in normalization will make a lot more sense. Before we get into the technical details, let's talk about why this matters, especially in healthcare. Poor database design leads to redundant data. The same information gets stored in multiple places. When that happens, inconsistencies creep in. One record says a patient lives at 123 Main Street. Another says 123 Main ST period. And a third says 124 Main Street. Which one's correct? Nobody knows. In healthcare, these inconsistencies aren't just annoying, they're dangerous. Consider a primary care setting where a patient's medication allergy is recorded in multiple places. Well, if one record is updated but others aren't, a provider might prescribe a medication that causes an allergic reaction. Similarly, billing errors can occur when a patient's demographics don't match across all systems. Duplicate patient records lead to fragmented care. The goal of good database design is to minimize redundancy while preserving the relationship between data. We want each fact stored exactly once, in exactly one place. When we need to update something, we update it in one location, and the changes reflected everywhere that fact might be utilized. The systematic approach to achieving this goal is called normalization, and is based on understanding functional dependencies. Now let's define our key concept, the functional dependency. A functional dependency exists when one attribute uniquely determines another attribute. We write this as A and then an arrow that points to B, which we read as A determines B, or A functionally determines B. What does this mean in plain English? It means that if I know the value of A, I can look up exactly one value of B. There's no ambiguity. A points to one and only one B. In this notation, A is called the determinant. It is the attribute doing the determining. B is called the dependent. Its value depends on A. Here's a simple example from everyday life, your Social Security number. It determines your name. If I know your Social Security number, I can look up exactly one legal name associated with it. Social Security number pointing to a name is a functional dependency. Note that the reverse isn't necessarily true. Your name doesn't determine your Social Security number because multiple people can have the same name, like John Smith doesn't uniquely identify one Social Security number. This concept of determines or uniquely identifies is the foundation of everything we'll discuss in normalization. Let's look at a concrete example from our X-Health primary care database. Here we have a simple patient table with patient ID, patient name, and date of birth, and primary care provider. Looking at this data, we can identify several functional dependencies. Patient ID determines patient name. If I tell you the patient ID is P001, you can look up exactly one name, Maria Garcia. There's no ambiguity. Patient ID determines date of birth. Patient P001 was born on March 15, 1985. Only one birth date for that patient. Patient ID determines the primary care provider. Each patient has one assigned PCP in our model. Notice that the patient ID is our determinant for all of these. This makes sense. The patient ID is our primary key, and primary keys should uniquely determine all other attributes in the table. That's exactly one of the rules of normalization that we will formalize a little later. Also notice that the primary care provider does not determine patient ID. Dr. Smith has multiple patients, like in this example P001 and P003. So knowing the provider doesn't tell you which specific patient you're looking at. Not all functional dependencies are created equal. Let's distinguish between types. A trivial functional dependency is one where the dependent is already part of the determinant. For example, if we have a composite attribute, patient ID, patient name, then patient ID, patient name determines patient ID. Well, of course it does. Patient ID is already in the set. This is always true and tells us nothing useful about our data design. We can ignore trivial dependencies. A non-trivial functional dependency is one where the dependent is not part of the determinant. Patient ID determines patient name is non-trivial because patient name isn't part of the ID. These are the dependencies that matter in normalization. Finally, a fully functional dependency means the dependent relies on the entire determinant, not just part of it. This becomes important when we have composite keys, keys that are made up of multiple attributes. If an attribute depends on only one part of a composite key, that's called a partial dependency. And it's a problem we'll address in second normal form. For now, just remember, we care about non-trivial dependencies and we want attributes to depend on the whole key. Right, let's map out the key functional dependencies in our X-Health database. Understanding these will help you see how a well-designed healthcare database should work. Patient ID determines name, date of birth, address, and phone. All patient demographic information is determined by the patient identifier. Know the patient, know their demographics. Encounter ID determines encounter date, provider ID, and clinical notes. Each encounter has one date, one responsible provider, and one set of documentation. Provider ID determines provider name, specialty, and NPI, the National Provider Identifier. That NPI is a unique 10-digit number that's assigned to healthcare providers. Each provider has only one. Medication ID determines the drug name, NDC code, and standard dosage forms. The National Drug Code uniquely identifies medications. And Diagnosis Code determines diagnosis description. For example, the ICD-10 code E11.9 always means type 2 diabetes without complications. The code determines the description. These dependencies will tell us how to structure our tables. Attributes that share the same determinant should generally be in the same table, and with that determinant as the primary key. Now that we understand functional dependencies, let's see what happens when we ignore them when we design databases poorly. The result is anomalies. Database anomalies are data inconsistencies that arise from redundant or improperly structured data. They make your database unreliable and difficult to maintain. There are three types. They're all related to data modification operations. Insertion anomaly. You can't add new data without also adding other, unrelated data. The database structure forces you to invent fake data or leave required fields null. Update anomaly. The same data is stored in multiple places, so when you need to change it, you have to find and update every copy. Miss one, and your database is inconsistent. Or a deletion anomaly. When you delete data, you unintentionally lose other information that was stored in the same row. All three anomalies stem from the same root: redundancy combined with poor table structure. Let's look at each one in detail. An insertion anomaly occurs when you cannot insert new valid data because the table structure requires other data that doesn't exist yet. Think about this from the primary care perspective. Imagine your clinic hires a new physician, Dr. Lee. She's credentialed, has her NPI, and she's ready to see patients, but she hasn't had any patient encounters yet because she just started. Your database stores provider information only in an encounters table. You literally cannot add Dr. Lee to the system. There's no encounter to attach her to. The table might have encounter ID as part of the primary key, and you can't have a null primary key. So what happens? Either you can't add the new provider until she sees her first patient, which is absurd from an operational standpoint, or someone creates a fake placeholder encounter just to get her into the system. Neither option is acceptable. The same problem occurs with insurance plans. If insurance information is stored only with patient records, you can't add a new insurance plan until someone enrolls in it. You can't add a new medication to your formulary until someone prescribes it. This is the insertion anomaly, valid real-world data that your database structure won't accept. The update anomaly is perhaps the most common problem in poorly designed databases. It occurs when the same fact is stored in multiple rows. When that fact changes, you have to update every single row that contains it. If you miss even one, your database now has contradictory information. Consider this primary care scenario. Dr. Smith's clinic moves from 123 Main Street to 456 Oak Avenue. If the clinic address isn't stored in every encounter record, and Dr. Smith has seen 5,000 patients over the years, you now have 5,000 rows that you have to update. What if your update query misses some of the rows? Maybe encounters from before 2020 are in an archive table that wasn't included. Now your database says Dr. Smith is at two different addresses depending on which encounter you look at. Or consider a patient's phone number. In a denormalized database, the phone number might be stored in the patient table, the insurance table, the emergency contact table, and repeated in every encounter. The patient calls to update their number. How many places does your staff need to remember to change it? This is why we say store each fact exactly once. If Dr. Smith's address is in exactly one row of a provider's table, updating it is trivial. One row, one change, done. The deletion anomaly is the most dangerous. because it results in permanent data loss. It occurs when deleting one piece of information inadvertently destroys another, unrelated information that was stored in the same row. Here's a healthcare example. A patient, James Wilson, came to your primary care clinic exactly once, 2 years ago, for an upper respiratory infection. His encounter record contains his demographics, the provider who saw him, Dr. Smith, and the diagnosis J06.9, which is upper respiratory infection unspecified. Now suppose James calls and invokes his right under HIPAA to have his record deleted. You delete his encounter. In a poorly designed database where provider information is embedded in encounter records, you might have just deleted the only record that shows Dr. Smith as a physician in your clinic, if James happened to be Dr. Smith's only patient in this example. Or consider medication data. If the only record containing information about a particular medication gets deleted because a patient withdrew consent, you've lost your formulary data for that drug. The deletion anomaly shows why data about different entities, patients, providers, medications, diagnoses, should be stored in separate tables. Deleting a patient should not affect your provider roster. So let's see all three anomalies in a single realistic example from our healthcare primary care database. Look at this unnormalized encounter table. It crams everything into one row. Encounter information, patient demographics, provider details, and diagnosis data, all in one row. Maria Garcia has 2 encounters with Dr. Smith, one for diabetes and one for hypertension. Notice how her name, phone number, and all Dr. Smith's information is duplicated across both rows. Now let's identify the anomalies. Insertion anomaly. When we want to add a new provider, Dr. Johnson, who hasn't seen any patients yet, we can't. There's no encounter to put him in. Update anomaly. Maria Garcia changes her phone number. We have to update 2 rows. If we miss one, which phone number is the correct one? And Dr. Smith's information is repeated in all 3 rows. If we need to update his NPI, we have 3 rows we have to change. Deletion anomaly. James Wilson has only 1 encounter. If we delete it, we lose the fact that diagnosis code J06.9 means upper respiratory infection. We also lose any record that Dr. Smith ever treated him, which might matter for continuity of care. This single table violates all 3 normal forms we're about to learn. The solution: decompose it into properly normalized tables. We've seen the problems. Now let's preview the solution: normalization. Normalization is a systematic step-by-step process for organizing database tables to eliminate redundancy and remove anomalies. It's not guesswork. It's based on rigorous analysis of functional dependencies. The process works through a series of normal forms, each with specific rules. Think of them as checkpoints. First normal form, or 1NF, addresses one set of problems. Second normal form, or 2NF, addresses another, and third normal form handles yet another. There are higher forms, BCNF, 4 normal form, 5 normal form, but 3 normal form is sufficient for almost all practical healthcare database applications. Each normal form builds on the previous one. You must achieve primary normal form before you can go to secondary normal form or second normal form, and you must be in second normal form before you can achieve third normal form. It's a progression. The normalization process follows these steps. 1. Identify all functional dependencies in your data. 2. Check with which normal form rules are violated. 3. Decompose tables to fix violations. 4. Establish relationships between the new tables using foreign keys. And 5th, verify that no anomalies remain. In Part 2, we'll walk through each normal form with detailed healthcare applications. So let's summarize what we've covered so far in Part 1. Functional dependencies describe how attributes relate to each other. The notation of A points to B means A uniquely determines B. These dependencies are the foundation of good database design. They tell us which attributes belong together in a table. We identified 3 types of anomalies that plague poorly designed databases. Insertion anomalies prevent us from adding valid data. We couldn't add a new provider without a fake encounter. Update anomalies force us to change the same data in multiple places. Miss one update and your database contradicts itself. Deletion anomalies cause unintended data loss. Deleting a patient encounter shouldn't delete provider or diagnosis information. These anomalies aren't just theoretical. In healthcare, they lead to patient safety issues, billing errors, and compliance problems. Normalization is a systematic solution. By analyzing functional dependencies and progressively applying normal forms rules, we can decompose problematic tables into well-structured ones that don't suffer from these anomalies. In Part 2, we'll learn exactly how to do this. We'll transform our problematic X-Health encounter table into a properly normalized set of tables. Welcome to Part 2. We will work together through the normalization process, step by step. We're going to transform messy, problematic data into clean, well-structured tables. And by the end of this section, you'll be able to take any unnormalized table and systematically bring it to third normal form. So let's get started. Let's formally define normalization. Normalization is the process of organizing data in a database to reduce redundancy and improve data integrity. The key word here is systematic. This isn't art, it's engineering. There are specific rules to follow. The process is organized into a series of normal forms. Each normal form has a name and a set of requirements. The main ones you'll encounter are first normal form, second normal form, third normal form, and Boyce-Codd normal form, BCNF. Each form builds on the previous one. A table in second normal form is automatically also in first normal form. A table in third normal form is automatically both second normal form and first normal form. It's cumulative. For most production healthcare databases, third normal form is the target. It eliminates the vast majority of redundancy and anomalies while keeping the database design manageable. Higher normal forms exist, but are rarely needed in actual practice. The trade-off with normalization is that you end up with more tables. Your one giant table might become 5 or 6 smaller tables. This means more join statements when querying, but the benefits, data integrity, easier maintenance, no anomalies, far outweigh the cost of writing slightly more complex queries. Let's look at the hierarchy of normal forms and what each one accomplishes. First normal form requires that all values be atomic. No lists, no repeating groups, no multiple values stuffed into a single cell or column. First normal form eliminates multi-valued attributes and ensures every cell contains exactly one value. Second normal form builds on first normal form by requiring that there are no partial dependencies. Every non-key attribute must depend on the entire primary key, not just part of it. This matters when you have composite keys, keys that are made of multiple columns. Second normal form eliminates partial dependencies. Third normal form builds on second normal form by requiring no transitive dependencies. Non-key attributes cannot depend on other non-key attributes. Everything must depend directly on the primary key in that table. So third normal form eliminates transitive dependencies. And Boyce-Codd normal form is a stricter version of 3NF. It requires that every determinant be a candidate key. In practice, most third normal form tables are also in Boyce-Codd normal form, so we won't spend too much time discussing that. There's a helpful memory device. A table in third normal form depends on the key, the whole key, and nothing but the key. First normal form gives us the key. Second normal form ensures the whole key, and third normal form ensures nothing but the key. Well, let's look at a hierarchy of normal forms and what each one accomplishes. First normal form requires that all values be atomic. No lists, no repeating groups, no multiple values stuffed into a single cell. First normal form eliminates multi-valued attributes and ensures every cell contains exactly one value. Second normal form builds on first normal form by requiring that there are no partial dependencies. Every non-key attribute must depend on the entire primary key, not just part of it. This matters when you have composite keys, keys that are made up of multiple columns. Second normal form eliminates partial dependencies. And third normal form builds on second normal form by requiring no transitive dependencies. Non-key attributes cannot depend on other non-key attributes. Everything must depend directly on the primary key. So third normal form eliminates transitive dependencies. And your Boyce-Codd normal form is a stricter version of the third normal form. It requires that every determinant must be a candidate key. In practice, most third normal form tables are also in Boyce-Codd normal form, so we won't spend too much time on that. Here's a realistic example of unnormalized data from our X-Health primary care setting. Let's look at this table. Maria Garcia has 3 medications listed in a single cell: metformin 500 milligrams, lisinopril 10 milligrams, alvastatin 20 milligrams. James Wilson has 2. Sarah Chen has 1. What's wrong with this? Several things. First, the medications column is not atomic. It contains multiple values. If someone asks how many patients are on metformin, you can't easily answer that question. You'd have to parse through comma-separated strings, which is error-prone and slow. Second, there's no room for medication-specific data. When did Maria start metformin? What's the NDC code? Has the dosage changed? There's nowhere to put this information. Third, searching and filtering is nearly impossible. A query like select star where medication equals metformin 500 milligrams won't find Maria's record because her medication field contains more than just metformin. And fourth, updates are complex. If Maria discontinues lisinopril, you have to parse the string, remove the lisinopril, and reconstruct the string. That's application logic that the database should be handling. This data needs to be in first normal form. Let's establish the rules for first normal form. Rule 1. Eliminate repeating groups. You should not have columns like diagnosis 1, diagnosis 2, diagnosis 3. If you need multiple values, they should be in separate rows, not separate columns. Rule 2. Each cell contains only atomic values. Atomic means indivisible, one value per cell. Metformin 500 milligrams, lisinopril 10 milligrams is not atomic. Metformin 500 milligrams is atomic. If you can meaningfully split a value, it's not atomic. And rule 3, each column has a unique name. You can't have 2 columns both called phone. This seems obvious, but comes up when people add phone 2 and forget to rename the original. Rule 4, each row is uniquely identifiable. There must be a primary key, 1 or more columns that uniquely distinguish every row. Rule 5, the order of rows and columns doesn't matter. The database shouldn't depend on physical ordering. Data is identified by values, not positions. So when a table satisfies all 5 rules, it's in first normal form, and this is the foundation. You cannot proceed to second normal form without first achieving first normal form. There are 2 common methods to convert unnormalized data to first normal form. And let's look at the first, creating separate rows for each value. Looking at our before example, Maria Garcia has 2 medications in one cell. In method 1, we split this into 2 rows, one for each medication. Now every cell contains exactly 1 atomic value. Maria Garcia appears twice, once for metformin and once for lisinopril. The multi-valued attribute problem is solved. But wait, we've introduced a new problem. The patient name is now repeated. If Maria changes her name, we have to update 2 rows. So we've traded one problem for another. This brings us to an important point. Primary normal form solves the atomicity problem, but may introduce redundancy. That's okay, we'll fix the redundancy in second normal form and third normal form. Also, notice that our original primary key, patient ID alone, no longer works. Maria has 2 rows with patient ID P001. We now need a composite key, perhaps patient ID, medication, to uniquely identify each row. Method 1 is quick, but often creates partial dependencies that we will need to resolve. Method 2 is generally better. Instead of repeating patient information, we create a separate table for the multi-valued attribute. We split the original table into 2 tables. The patient's table contains the patient ID and name, date of birth. Each patient appears exactly once. The patient medications table contains the patient ID, medication name, and dosage, with 1 row per medication per patient. So patient ID appears in both tables. In the patient's table, it's the primary key. But in the patient medications table, it's a foreign key that references the patient table. This approach has several advantages. Patient information is stored exactly once. Change Maria's name in one place, and it's changed everywhere we want to reference it. The medications table can grow independently. Add as many medications as needed without affecting the patient record. We can add medication-specific attributes like start date, end date, prescriber ID to the medications table without touching the patient table. This is the preferred approach to achieving first normal form. Decomposition into multiple tables connected by foreign keys is the essence of normalization. Let's look at another common healthcare scenario, encounter diagnoses. In the before state, we have an encounters table where the diagnosis column contains multiple ICD codes, for example, E11.9, I10, E78.5, all concatenated into one cell. This is classic unnormalized data. Unacceptable. To convert to primary normal form, we create a separate encounter diagnosis table. The encounters table keeps the encounter ID and the patient ID, and the encounters diagnosis table has encounter ID and diagnosis code with 1 row per diagnosis. Encounter E001 had 3 diagnoses, so it gets 3 rows in the encounter diagnosis table. Each row contains exactly 1 atomic diagnosis code. Now we can easily query find all encounters with diabetes becomes a simple where clause. Count diagnoses per encounter is a straightforward group by query. This pattern of decomposing a multi-valued attribute into a separate table is fundamental to primary normal form, first normal form, and comes up constantly in healthcare databases. Patients have multiple allergies. Encounters have multiple procedures. Providers have multiple specialties. Each of these should be in separate tables. Before moving on to second normal form, let's verify that our table is truly in first normal form. Let's ask yourself these 3 questions to test. Are all values atomic? Check each cell. Is there any cell containing a list or a comma-separated field of values, or multiple items? If yes, you have not gotten into primary normal form, first normal form. Are there any repeating groups? Look at your column names. Do you see diagnosis 1, diagnosis 2, diagnosis 3, or home phone, work phone, cell phone? These repeating columns indicate you're not in primary normal form. Is there a primary key defined? Can you uniquely identify every row? If you have duplicate rows or no clear identifier, you're not in primary normal form. Is each column uniquely named? A technical requirement, but important. If you can answer yes to all of these, your table is in first normal form and you're ready to analyze it for second normal form. If any answer is no, go back, fix those issues first. Remember, you cannot be in second normal form without first being in first normal form. Second normal form, the rules. This addresses a specific problem, partial dependencies. First, the prerequisite. Your table must already be in first normal form. If it's not, go back and fix that. The second normal form rule is no partial dependencies. Every non-key attribute must depend on the entire primary key, not just part of it. When does this matter? Only when you have a composite primary key, a key made of multiple columns. If your primary key is a single column and you're in first normal form, you're automatically in second normal form. But a partial dependency can occur when there's a multi-part key to be partial about. Here's what a partial dependency looks like. You have a composite key, A and B, and attribute C depends only on A, but not on the combination of A and B. So C partially depends on the key. For example, if your key is order ID and product name depends only on the product ID, that's a partial dependency. Product name doesn't care about order ID. It's determined entirely by which product you're looking at. So the solution is to partial dependencies is a decomposition, split the table, so that the attributes move to tables where they depend on the whole key. Let's look at a concrete healthcare example of partial dependency. This table tracks which diagnoses were recorded at each encounter. The composite primary key is encounter ID, diagnosis code. Together these identify a unique row. Now let's look at the non-key attributes. Encounter date depends only on encounter ID. If I tell you the encounter ID is E001, you know the date was January 15th, 2026. You don't need to know the diagnosis code to determine the date. This is a partial dependency. The encounter date depends on part of the key. Diagnosis description depends only on the diagnosis code. The description type 2 diabetes mellitus is determined entirely by code E11.9. It doesn't matter which encounter you're looking at. E11.9 always means diabetes, another partial dependency. Notice the redundancy this creates. Type 2 diabetes mellitus appears twice because E11.9 was diagnosed in 2 encounters. The January 15th appears twice because encounter 1 had 2 diagnoses. So if the description of E11.9 changes, say to match a new ICD addition, we'd have to update multiple rows and update anomaly. This table violates second normal form. To convert to second normal form, we decompose the table to eliminate partial dependencies. We create 3 tables, each focused on one entity. The counters table has encounter ID as its primary key with encounter date as an attribute. Now encounter date depends on the whole key, which happens to be just the encounter ID. The diagnosis table has diagnosis code as its primary key with diagnosis description as an attribute. Now diagnosis description depends on the whole key. The encounter diagnosis table is a junction table With a composite primary key, composed of the encounter ID and diagnosis code, it has no non-key attributes. It simply records which diagnoses occurred at which encounters. This is a classic many-to-many relationship implementation. One encounter can have multiple diagnoses. One diagnosis can appear in multiple encounters. The junction table captures these associations. Now each fact is stored once. The description type 2 diabetes appears in exactly one row in the diagnosis table. Update it there, and it's updated everywhere that it's referenced. Here's another healthcare example, prescriptions. In the before table, we were tracking prescriptions with a composite key of prescription ID, medication ID. Let's say each prescription can have multiple medications, and this item tracks each item. Medication name and drug class depend only on medication ID. Whether this is prescription RX001 or RX002 doesn't affect the fact that Med01 is metformin, and it's biguanide. These are partial dependencies. Look at the redundancy. Metformin and biguanide appear twice because two prescriptions include that medication. So to convert to second normal form, we create a medications table with medication ID as the key, containing medication name and drug class. The prescriptions table keeps prescription-specific information like patient ID and dosage, which might vary per prescription. Now medication ID in prescriptions is a foreign key referencing medications. Each medication's name and class is stored exactly once. This design also makes it easy to add medication-specific attributes later, like the NDC code or manufacturer or warnings, without touching the prescription records. Before moving on to third normal form, verify that your table meets second normal form requirements. First, check is the table in first normal form. If not, you can't be in second normal form. Go back and fix atomicity issues first. If your table has a single column primary key, you're automatically in second normal form. Partial dependencies can only exist with composite keys. A single column can't be partially depended upon. If you have a composite primary key, ask, does every non-key attribute depend on the full key? Or do some attributes depend only part of the key? The test is simple. For each non-key attribute, ask, do I need to know all parts of the key to determine this value, or just some parts? If any attribute depends only on part of the key, you have a partial dependency. Decompose the table. Move that attribute to a new table where it depends on the full key of that new table. When all non-key attributes depend on the complete primary key, you're in second normal form and ready for third normal form analysis. Third normal form tackles the last major category of problematic dependencies, transitive dependencies. The prerequisite, your table must be in second normal form. We've eliminated repeating groups and partial dependencies, but now we address transitive dependencies. The third normal form rule, no transitive dependencies. Non-key attributes cannot depend on other non-key attributes. Every non-key attribute must depend directly on the primary key for that table. What's a transitive dependency? It's a chain. The primary key determines attribute A, and A determines attribute B, so B depends on the primary key, but indirectly through A. The classic example, employee ID determines department ID, and department ID determines department name, so employee ID determines department name, but transitively through department ID. The problem? Department name is really a fact about departments, not about employees. It's being stored in the employees table because of the chain of dependencies. This creates redundancy. Every employee in the same department has the same department name stored in their row. The solution? decompose. Move department name to a departments table where it depends directly on department ID. Let's trace through a transitive dependency in detail. This table lists healthcare providers. Provider ID is the primary key. Look at the dependency chain. Provider ID determines specialty. Dr. Smith has specialty ID SP01. If you know the provider, you know their specialty ID. Specialty ID determines specialty name. SP01 is family medicine. The specialty ID determines the name. Therefore, provider ID determines specialty name, but not directly. It goes through a specialty ID, and this is a transitive dependency. The primary key goes to A, then goes to B. See the redundancy? Family medicine appears twice because two providers have specialty SP01. If the specialty name changes, maybe to family and community medicine, we would have to update multiple rows. The issue is that specialty name is a fact about specialties, not about providers. It's in the wrong table. The dependency diagram would show provider ID goes to specialty ID goes to specialty name. That middle arrow between the two non-key attributes is the transitive dependency we need to eliminate. To eliminate the transitive dependency, we decompose into two tables. The providers table keeps provider ID as the primary key, with provider name and specialty ID as attributes, but the specialty ID is now a foreign key. The specialties table has specialty ID as the primary key, with specialty name as an attribute. Now let's trace the dependencies. In providers, provider ID goes to provider name, a direct dependency, no problem. Provider ID goes to specialty ID, direct dependency, again, no problem. But in specialties, specialty ID goes to specialty name, that's a direct dependency. There's no longer a transitive chain within any single table. Each non-key attribute depends only on its table's primary key. Specialty name is stored exactly once per specialty. Family medicine appears in one row in the specialties table, not repeated across multiple provider records. Change the specialty name once in one row, and all providers with that specialty automatically reflect the new name through that foreign key relationship. This is the power of third normal form. Every fact is stored exactly once in the table where it belongs. Here's a common healthcare scenario that often violates third normal form: patient insurance information. In the before table, we have patients with their insurance details. Patient ID is the primary key. Check the dependency chain. Patient ID goes to insurance ID. Each patient has one insurance plan. Insurance ID goes to insurance name, plan type. The insurance ID determines the name and type. So patient ID goes to insurance ID, goes to insurance name. That's a transitive dependency. Look at the redundancy. Blue Cross South Carolina and PPO appear twice because patients P001 and P002 share the same insurance plan. But if Blue Cross changes its name, maybe after a merger, you have to update multiple patient records. That's an update anomaly caused by the transitive dependency. The solution? Create an insurance plans table with insurance ID as the primary key. Move insurance name and plan type there. In the patients table, insurance ID becomes a foreign key. Now insurance information is stored once per plan, not once per patient. Much cleaner, much more maintainable. Let's verify that a table meets third normal form requirements. First, is it in second normal form? Remember, third normal form builds on second normal form. Verify there are no partial dependencies. Second, check for transitive dependencies. For each non-key attribute, ask, does this attribute depend on another non-key attribute? If attribute's B value can be determined by knowing attribute A, and A is not a key, then you have a transitive dependency. Your primary key goes to A, goes to B. The fix is always the same. Decompose. Create a new table with A as the primary key and B as an attribute. In the original table, keep A, but make it a foreign key referencing the new table. When no non-key attribute determines another non-key attribute, and all non-key attributes depend directly on the primary key, you're in third normal form. You've succeeded. There's a famous mnemonic. When taking an oath in court, you swear to tell the truth, the whole truth, and nothing but the truth. Well, for third normal form, every attribute must depend on the key, the whole key, and nothing but the key. The key, in first normal form, there is a key. The whole key, in second normal form, there's no partial dependencies. And nothing but the keys in third means you're in third normal form. There are no transitive dependencies. So let's put it all together with a complete example. We'll take a badly designed X-Health encounter table and normalize it step by step. Here's our starting point, a single unnormalized table with everything crammed in. Patient demographics, provider information, specialty details, diagnoses, all in one row. The problems are numerous. The diagnoses contain multiple values. That violates first normal form. Patient name depends on patient ID only, not the full record. Ready for second normal form issues. Specialty name depends on specialty ID, not provider ID. So we have a transient dependency that violates third normal form. So after full normalization, we have 5 tables. We have the patients with the patient ID as its primary key, and it has patient name, patient phone, providers, and then the providers use the provider ID as the primary key. You've got the provider file, which has the provider ID as the primary key, and you've got provider name and specialty. Specialty ID is a foreign key. In the specialties table, you have specialty ID as the primary key and specialty name. In the encounters table, you have encounter ID as the primary key, patient ID as the foreign key, provider ID as a foreign key. Then you also have encounter date, encounter diagnoses. Then you have the encounter diagnosis file, which includes encounter ID as the foreign key, diagnosis code as a foreign key, and it's only a junction table. There's no other data in there. Each entity has its own table. Each fact is stored once. Foreign keys maintain the relationships. This structure eliminates all 3 anomaly types. We can add providers without encounters. We can update specialty names in one place and delete encounters without losing provider data. Let's compare before and after to really appreciate what normalization accomplishes. Before, we had one large table with everything. After, we have 5 focus tables. Before, we had patient and provider information repeated across many rows. After, each fact is stored exactly once. Before, we can't add a provider without creating an encounter. After, we can add providers independently to the providers table. Before, changing a phone number means updating multiple rows. After, one row to update in the patients table. Before, deleting an encounter might lose provider information. After, we have safe deletion. Foreign key relationships prevent orphans. Before, we had simple queries but limited flexibility, but after, joins are required, but queries are far more flexible and the results are consistent. Before, application code must enforce data integrity. After, database constraints enforce integrity automatically. The trade-off is complexity. You have more tables, more relationships, and queries require joins, but this complexity is managed, structured complexity. The alternative, unmanaged chaos, in a denormalized table is far worse for maintenance. In healthcare systems that must maintain data for years or decades, this maintainability is essential. After spending all this time on normalization, I need to tell you, sometimes you intentionally don't normalize, or you deliberately denormalize an already normalized database. When would you do this? Reporting and analytics databases. If your database is primarily read and rarely written, the anomaly risks are lower. Denormalized tables mean fewer joins, which means faster queries. Business intelligence dashboards often use denormalized data. Data warehouses. Star schemas and snowflake schemas are specifically designed patterns that intentionally include redundancy for query performance. The fact table in the center connects to denormalized dimension tables. Caching layers. Sometimes you pre-compute and store redundant data to speed up common queries. The redundancy is controlled and updated programmatically. In healthcare specifically, patient summary dashboards that show everything on one screen, population health reports that aggregate data across thousands of patients, and real-time clinical decision support that needs sub-second response times. The rule of thumb: normalize for online transaction processing, OLTP, your operational systems that handle day-to-day data entry. Consider denormalization for OLAP, online analytical processing, your reporting and analytics systems. But for the X-Health database that clinicians use daily, normalize to third normal form. For the reporting database that executives query for trends, strategic denormalization is acceptable. After spending all this time on normalization, let's summarize the normalization process. First normal form ensures atomic values, eliminates repeating groups. Every cell holds one value. Every row is unique. This solves the problem of multi-valued attributes. Second normal form eliminates partial dependencies. Every non-key attribute depends on the complete primary key, not just part of it. This matters when you have composite keys. Third normal form eliminates transitive dependencies. Non-key attributes cannot depend on other non-key attributes. Everything depends directly on the primary key. Together, these three normal forms eliminate the anomalies we discussed: insertion, update, and deletion anomalies. They become non-issues when the data is properly normalized. The trade-off is more tables and more joins, but this structured complexity is far easier to manage than the chaos of denormalized data with its hidden redundancy and lurking anomalies. The memory device depends on the key, the whole key, and nothing but the key. Remember that. In Part 3, we'll see how to enforce these design principles at the database level using integrity constraints. We've designed good tables, and now let's make the database reject bad data automatically. Part 3, Data Integrity Constraints. Welcome to Part 3, where we move from design theory to practical implementation. We've learned how to design normalized tables that avoid anomalies. But design is just a blueprint. How do we ensure that the database actually enforces our design? How do we prevent bad data from entering in the first place? The answer is integrity constraints. These are rules built into the database that automatically validate data and reject anything that violates the rules. Let's explore how to implement them in Postgres. Integrity constraints are rules defined in the database schema that ensure data accuracy and consistency. They're enforced automatically by the database management system, not by application code, not by user discipline, but by the database itself. When you try to insert, update, or delete data, the DBMS checks whether the operation would violate any constraints. If it would, the operation is rejected with an error. the invalid data never enters the database. This is crucial because it creates a safety net. Even if your application has a bug, or even if a developer writes a bad query, even if someone connects directly to the database with an SQL tool, the constraints still protect data integrity. In healthcare, this matters enormously. Patient safety depends on data quality. You can't have a medication order with an invalid patient ID. You can't have a null value where a diagnosis code is required. You can't have two patients with the same medical record number. Constraints encode these business rules in the database itself, creating a foundation of data quality that all applications built on top of can rely on. There are four main types of integrity constraints in relational databases, and let's examine each one. And the four types of integrity constraints address different aspects of the data quality. There are domain constraints. They define what values are valid for each column. They specify data types, acceptable ranges, and formats. Like age must be between 0 and 120 is a domain constraint. Entity integrity ensures that every row can be uniquely identified. It requires that primary keys are unique and not null. Without entity integrity, you can't reliably distinguish one record from another. Referential integrity maintains valid relationships between tables. It ensures that foreign keys point to actual existing records. You can't have an encounter that references a patient who doesn't exist. Key constraints enforce uniqueness for identifying attributes. Beyond the primary key, you might have other columns that must also be unique, like Social Security number or National Provider Identifier. These four types work together to create a comprehensive data quality framework. Domain constraints validate individual values. Entity integrity validates row identity, and referential integrity validates relationships. Key constraints validate uniqueness. All right, let's look at each in a little more detail. Domain constraints. They define the valid domain, the set of acceptable values for each column in your database. The most basic domain constraint is the data type. When you define a column as an integer, you're saying it can only hold whole numbers. If you define it as a date, then it must be a valid date. If you define it as varchar 50, it can hold text up to 50 characters. But data types alone aren't enough for healthcare. Technically, 500 is a valid integer, but it's not a valid age. January 50th isn't a valid date, but the database won't let you enter it anyway. We need additional constraints. Value ranges constrain numeric data to sensible bounds. In primary care, blood pressure, systolic between 60 and 250, diastolic between 40 and 150, temperature between 90.0 Fahrenheit to 110 degrees Fahrenheit. Values outside this range indicate a measurement error usually, or a critical patient condition. Weight must be a positive number. Age 0 to 120 years. Format constraints ensure data follows expected patterns. Phone numbers should match a specific format. Email addresses should have an @ sign in them. Enumeration constraints limit values to a specific list, like gender might be limited to M, F, or O, or U for unknown, following the HL7 standards. A status might be active, inactive, or deceased. Let's see how to implement domain constraints in Postgres. Look at this create table statement for a patient table. The patient ID column is a variable character of 10 digits, and also primary key. So we specify that that's going to be the primary key. The varchar 10 is the domain constraint, limiting it to 10 characters. First name and last name are varchar 50, not null. The not null is a domain constraint. These fields cannot be empty. Every patient must have a name. Date of birth is date, not null. It must be a valid date, and it must be present. Gender is char 1 with a check constraint limiting it to values M, F, O, or U. If you try to insert X, the database will reject it. Email has a check constraint. With a like pattern, it must contain an @ symbol followed by a dot. This is simple email validation. Not comprehensive, but it catches some of your obvious errors. The named constraint, valid date of birth, uses check to ensure birth dates are between 1900 and today. No patients born before 1900, and no future birthdays. When anyone tries to insert data that violates these constraints, Postgres returns an error and the insert fails. The bad data never enters the database. Entity integrity is fundamental to relational databases. It ensures that every row in a table can be uniquely identified. The rule is simple. The primary key cannot be null, must be unique. Why can't it be null? Because the primary key is how we identify rows. If a patient ID is null, which patient are we talking about? We can't answer basic questions like what medications is this patient taking? We can't identify the patient. Why must it be unique? Because duplicate keys mean duplicate identities. If two rows have patient P001 and we write a prescription for P001, which patient gets a medication? Both? Neither? System's broken. In healthcare, the consequences of violating data integrity are severe. Every patient must have a unique identifier, otherwise medical records get merged incorrectly, medications go to wrong patients, and billing becomes a nightmare. Every encounter must be traceable. If encounters can't be uniquely identified, you can't track what happened to a patient. Every medication order must be attributable. The prescriber, the patient, the date, the drug, all must be linked to specific identifiable records. And primary keys are the foundation. Without them, a relational database cannot exist, cannot function. Let's see entity integrity in Postgres. There are two ways to define a primary key. Method 1 is inline, right in the column definition. Patient ID, variable character 10, primary key. This is concise and works well for single column keys. Method 2 uses a separate constraint clause. Primary key, open parentheses, encounter ID, comma, diagnosis code. This is required for composite keys and can also be used for single column keys when you want to name the constraint. Once a primary key is defined, the database automatically enforces entity integrity. Attempting to insert a null primary key fails. The insert statement with null for patient ID returns an error like error, null value in column patient ID violates not null constraint. Attempting to insert a duplicate primary key fails also. If P001 already exists, inserting another P001 returns error, duplicate key value violates unique constraint. You don't have to write code to check these conditions. You don't have to trust that applications will validate data correctly. The database itself prevents invalid data at the most fundamental level. This is why entity integrity is enforced by the DBMS, not by application logic. It's too important to leave to chance. Referential integrity maintains the validity of the relationships between tables. The rule, a foreign key must match an existing primary key in the reference table, or it must be null if nulls are allowed. Why does this matter? Without referential integrity, you can have orphan records, records that reference non-existing parents. Imagine an encounter with patient ID P999, but no patient with ID P999 exists. Whose encounter is this? What are their allergies? What's their medical history? The data is meaningless. Worse than meaningless, it's misleading. In healthcare, referential integrity ensures that every encounter belongs to a real patient. You can't accidentally create encounters for patients who don't exist. Every prescription references a valid provider. Someone is accountable for every medication order. Every diagnosis links to a valid encounter. Clinical data is connected in meaningful ways. The alternative, allowing dangling references, creates data that looks complete but is actually broken. Records would show encounters with unknown patients. Analytics would count phantom records. Worse, clinical workflows could fail silently when trying to look up patient information that doesn't exist. Let's implement referential integrity in Postgres. First, we create the parent table, the one being referenced. Patients is our parent table with patient ID as its primary key. Then we create the child table, the one that references the parent. Encounters has its own primary key, encounter ID, and a foreign key, patient ID, that references the parent. The foreign key constraint specifies the relationship foreign key, patient ID, references, patients, and the column patient ID. This tells Postgres the patient ID in this table must match the patient ID that exists in the patients table. Now, if someone tries to insert an encounter with patient ID P999, but P999 doesn't exist in the patients table, Postgres rejects the insert. Error. Insert or update violates foreign key constraint, foreign key patient. The encounter is not created. The orphan record is prevented. Similarly, if you try to delete a patient who has encounters, Postgres will, by default, prevent the deletion. You can't leave encounters orphaned. This bidirectional protection, preventing invalid inserts into children and invalid deletes from parents, is the power of referential integrity. When you define a foreign key, you can specify what happens when the reference row is deleted or updated. These are called cascading actions. On delete restrict is the default. If you try to delete a patient who has encounters, the database refuses. You must first delete or reassign the encounters, and then delete the patient. This is the safest option and is appropriate for most healthcare scenarios. On delete cascade, automatically deletes child records when the parent is deleted. Delete a patient and all their encounters are automatically deleted too. This is rarely appropriate in healthcare due to audit and compliance requirements. Typically don't want to accidentally delete years of medical history. On delete set null, sets the foreign key to null when the parent has been deleted. The encounter would remain, but its parent ID would become null, an orphan, but a known orphan. This might be appropriate for truly optional relationships. On update cascade, automatically updates foreign keys when the primary key changes. If a patient's ID changes from P001 to P001-A, all encounters are automatically updated, and this can be very useful for identifier corrections. For healthcare databases, the general best practice is on delete restrict. Deleting a patient should be a deliberate multi-step process that ensures compliance with retention requirements, not something that happens automatically. HIPAA and other regulations often require maintaining records for specific periods. Cascade deletes could accidentally violate these requirements. Beyond primary keys, you often have other columns that must be unique. Key constraints handle these cases. Primary key, you can have only one per table. It's unique, cannot be null. It's the main identifier for that table. Unique, you can have multiple unique constraints per table. They ensure no duplicate values, but do allow null unless combined with not null specifically. These are for secondary unique identifiers. Not null ensures a column cannot be empty, often combined with unique for columns that are required and must be unique. So in healthcare, many identifiers should be unique. The National Provider Identifier, NPI. Every healthcare provider in the U.S. has a unique 10-digit NPI. Your providers table should have a unique constraint on the NPI. DEA number. Providers authorized to prescribe controlled substances have a DEA number. It should be unique, but nullable. Not all providers have one. Medical record number. Within your system, each patient's medical record number must be unique. Social Security number. If you collect Social Security numbers, they should be unique within your database. Though for privacy reasons, many systems avoid storing this nowadays. Looking at the SQL example, provider ID is the primary key, NPI is unique, not null. Every provider must have one, and no duplicates. DEA number is unique, but nullable. Only prescribers have one, but those who do must have unique numbers. Not every prescriber has one. Let's summarize integrity constraints we've covered. Domain constraints validate individual values. They enforce data types, acceptable ranges, formats, and enumerations. In Postgres, you implement these with data types, check constraints, and not null constraints. Entity integrity ensures that every row is identifiable. The primary key must be unique and not null. Without entity integrity, you cannot reliably work with your data. Referential integrity maintains valid relationships. Foreign keys must reference existing primary keys. This prevents orphan records and maintains the connections between the related tables. Key constraints enforce uniqueness. Beyond the primary key, unique constraints ensure that other identifying columns like NPI or MRN have no duplicates. And together these constraints implement the normalization rules we discussed earlier. Normalization is the design principle. Constraints are the enforcement mechanism. The beauty of constraints is automatic enforcement. You design the rules once in the schema definition. From then on, the database enforces them on every insert, update, and delete. Bad data is rejected before it can enter the database. In Part 4, we'll connect these concepts to HIPAA, de-identification, how database design supports privacy compliance. All right, here's our last section for today, Part 4, HIPAA de-identification. We've covered functional dependencies, normalization, and integrity constraints. These concepts help you to design databases that maintain data quality and prevent anomalies. Now we'll connect these technical concepts to a crucial healthcare requirement, HIPAA compliance and de-identification. As health informatics professionals, you'll frequently need to share or analyze patient data for research, for quality improvement, and public health purposes. HIPAA's de-identification requirements determine when and how you can do this. Good database design makes de-identification much easier. Let's explore this connection. Why do we need to think about de-identification when designing databases? Well, healthcare generates enormous amounts of valuable data. Researchers want to study disease patterns. Quality improvement teams want to measure outcomes. Public health officials want to track epidemics. All of these use cases require patient data. But patient data is protected by HIPAA. The privacy rule restricts how protected health information can be used and disclosed. Unauthorized disclosure can result in significant penalties, both financial and reputational. De-identification offers a path forward. Data that has been properly de-identified is no longer considered protected health information under HIPAA. It can be used for research, shared with partners, or published in studies without violating privacy concerns. In primary care settings, common use cases include quality improvement studies. How effective is our diabetes management program? You need data about patient outcomes, but not patients' identities. Population health analytics. What are the health trends in our patient population? Aggregate data answers this without identifying individual patients. Medical records, medical research, clinical trials, and observational studies often need de-identified data from multiple sites. Public health reporting. Disease surveillance requires sharing data with health departments, often in de-identified form. If your database is well designed, de-identification is straightforward. If it's poorly designed, with identifiers mixed into clinical data, de-identification becomes a complex, error-prone process. Before discussing de-identification, we need to understand what we're de-identifying. Protected health information, PHI, is defined by HIPAA as individually identifiable health information that relates to the past, present, or future physical or mental health condition of an individual, the provision of healthcare to an individual, the past, present, or future payment for healthcare. And this is crucial. It must identify the individual or provide a reasonable basis for identification. Here's the key insight. Identifiers alone are not protected health information. Health information alone is not protected health information. It's the combination that creates protected health information. A list of patient names is not protected health information. It's just a list of names with no health information attached. A list of diagnosis codes, again, not protected health information. It's just clinical information with no identifying information attached. But a list that shows Maria Garcia, E11.9 diabetes, that is protected health information. You've connected health information to an individual who's identified. De-identification breaks this connection by removing or obscuring the identifiers. You're left with health information that can't be linked back to an individual. That information is no longer protected health information and no longer subject to HIPAA's use and disclosure restrictions. HIPAA provides two approved methods for de-identification. Both produce data that is no longer considered PHI. The safe harbor method is rules-based. You remove all 18 specified identifiers from the data, and you have no actual knowledge that the remaining data could identify someone uniquely. If you follow the rules, you've achieved de-identification. The pros, it's very straightforward. Doesn't require special expertise. Anyone who can follow instructions can apply the safe harbor. The cons, you lose a lot of data utility. Removing all dates except year, for example, makes it impossible to study seasonal patterns or calculate time between events. The expert determination method is a risk-based technique. A qualified statistical expert analyzes data and certifies that the risk of re-identification is very small. The expert documents their methods and their justification. Pros, it's more flexible and preserves more data utility. An expert might determine that certain dates or locations can be safely retained. The cons, requires a qualified expert, which costs money, takes a lot of time. The expert must be genuinely qualified and must document their analysis. The choice depends on your specific needs. If you need quick, simple de-identification and can accept reduced data utility, use the safe harbor. If you need richer data and have resources for expert analysis, use expert determination. The safe harbor method requires removing these 18 specific identifiers. Let's go through them. Names, full names, maiden names, nicknames, any name that identifies the individual. Geographic data, anything more specific than state. Street addresses, cities, counties, zip codes must go. The exception is you can keep the first 3 digits of a zip code if that area has more than 20,000 citizens. Dates, all dates directly related to the individual must be reduced to year only. Birth dates, admission dates, discharge dates, death dates. Ages above 89 must be aggregated to 90 or older. Phone numbers, fax numbers, email addresses, all must be removed. Social Security numbers, obvious. That's an obvious unique identifier. Medical record numbers. These are internal identifiers that link to a patient's identity. Health plan beneficiary numbers, insurance ID numbers. Account numbers have to go. Certificate or license numbers, driver's license, professional licenses. Vehicle identifiers and serial numbers, including license plates. Device identifiers and serial numbers, like implanted medical devices. Web URLs, website addresses associated with that individual have to be deleted. IP addresses, network addresses associated with the patient have to be removed. Biometric identifiers, fingerprints, voice prints, retinal scans, face identification, they have to be removed. Full face photographs and comparable images, any image that could identify someone is impermissible. Any other unique identifying number, characteristic, or code, a catch-all for anything else that could potentially identify someone. This is a comprehensive list. You have to remove all of these, and then you've met the safe harbor, assuming that you also have no actual knowledge that the remaining data could ultimately identify someone. The expert determination method offers more flexibility, but it requires expertise. The requirement is that a person with appropriate knowledge of and experience with generally accepted statistical and scientific principles and methods for rendering information not individually identifiable must determine that the risk of identifying any individual is very small. HIPAA does not define what qualifications make someone an expert. However, OCR guidance suggests relevant expertise includes statistical training, practical experience, knowledge of re-identification risks and methods, understanding of what data might be available to potential attackers, experience with de-identification techniques like K-anomaly, L-diversity, or differential privacy. The expert must document the methods they used to analyze re-identification risk and the results of their analysis, and the justification for concluding that the risk is very small. This documentation must be retained. If your organization is ever audited, you need to show the expert's work. Again, the advantage of the expert determination is it preserves a lot of data, the data utility for research purposes. An expert might determine that keeping month and year, but not day, is acceptable for your specific data set, or that a 5-digit zip code is acceptable because your data covers a large, diverse population. But these decisions are all context specific. The disadvantage is cost and complexity. You need to find a qualified expert, pay for their analysis, and manage the documentation. So good database design makes de-identification much easier, and here are the key design principles. Separate identifier tables from clinical data. Don't store patient name and address in the same table as diagnoses and lab results. Create a patient demographics table for identifiers and a patient clinical table for clinical facts, linked by a surrogate key. Use surrogate keys, not natural identifiers. Don't use Social Security number or medical record number as primary keys. Generate synthetic identifiers, like patient ID, that have no meaning outside your system. When you de-identify, you can replace these synthetic IDs with random tokens. Design views that exclude identifiers. Create database views specifically for researchers or analysts that join clinical tables but exclude identifier tables. The view returns a useful clinical data table, but without any protected health information. Implement role-based access control. Clinicians who need to identify patients get access to identifier tables, but the researchers working with de-identified data get only access to the de-identified views. Looking at the SQL example, the research encounters view selects encounter and clinical data, but extracts only the year from the date of birth, so it's safe harbor compliant. Includes encounter date and diagnosis code, but does not include the patient name, date of birth, or address. Researchers query this view and never see identifiers. The database design enforces the separation. All right, well, let's see how it all connects. Let's step back and see how all of week 3's concepts connected. Functional dependencies are the foundation. By analyzing how attributes depend on each other, we understand our data's structure. We identify which attributes belong together and which should be separate. Normalization applies this understanding. We decompose tables to eliminate redundancy and anomalies. A normalized design stores each fact once in the table where it belongs. Importantly, for de-identification, normalization naturally separates different types of data. identifiers go in one table and clinical data in another. Integrity constraints enforce our design. Primary keys ensure every record is identifiable. Foreign keys maintain relationships between tables. Domain constraints validate data values. The database itself becomes a guardian of data quality. De-identification leverages all of this. A well-normalized database with clear separation between identifier and clinical tables is easy to de-identify. Create a view that excludes the identifier tables, apply safe harbor rules to remaining fields, and you have de-identified data ready for research use. Compare this to a denormalized mess where patient name, social security number, and diagnosis are all in one table, repeated across thousands of rows. De-identification requires finding and scrubbing identifiers throughout the data with a high risk of missing something. Good design isn't just about preventing anomalies, it's about enabling safe, compliant data use. So let's wrap up week 3 with a summary of what we've covered today. Functional dependencies, describing how attributes relate, like the notation if A points to B, means knowing A determines exactly one value of B. FDs are the theoretical foundation for normalization. Normalization is a systematic process of organizing data. First normal form has only atomic values, no repeating groups. Second normal form means there's no partial dependencies, and third normal form means there's not even any transitive dependencies. Each normal form eliminates a category of redundancy and the anomalies it could cause. Integrity constraints enforce our design at the database level. Domain constraints validate values. Entity integrity ensures identifiable rows. Referential integrity maintains valid relationships. Key constraints enforce uniqueness. And the HIPAA de-identification enables safe data sharing. The safe harbor method removes 18 identifiers. The expert determination method uses statistical analysis to certify low re-identification risks. Good database design with separated identifier and clinical tables makes de-identification straightforward. So your assignment this week is the normalization exercise. It's due February 2nd. You'll take unnormalized data and work through the process of converting it to third normal form, similar to what we did in this walkthrough. You'll also write up a reflection post on de-identification. The specifics are posted on Blackboard. Next week, we're going to dive into the SQL fundamentals, specifically the data definition language. Commands like create, alter, and drop. You'll learn to implement the designs that we've discussed, creating tables with proper constraints in Postgres. We'll also cover health information standards like HL7 and FHIR. Thank you for your attention this week. The concepts we covered are foundational, and they'll inform everything else you do in database design and management this semester. Thank you so much.